In section 4.3, we look at logarithmic functions. Let's start with the definition of a logarithm. For this, we will assume that a is a positive number and that a is not equal to 1. If x is a positive number, then we say the logarithm of x with respect to the base a, and that is denoted by y equals log base a of x, is defined to mean that x is equal to a to the y. So this equation here and this equation here are equivalent. And the number a is known as the base. What I would like to do is show you kind of a way to remember that these mean the same thing. So if we have log base a of x is equal to y, in exponential form, we can convert this by using the following little diagram. We start with the base a. We're going to jump over to the other side and raise it to the y power, and then loop back around and set it equal to x. So what we mean here is a to the y power is equal to x. These are equivalent statements. In other words, these mean exactly the same thing. And we'll do some examples here in just a minute. Now, in addition to understanding the basic definition of a logarithm, we also have an inverse property of logarithms. And it basically says the following. If you take the number a and you raise it to the power log base a of x, you just get x. So in a way, what happens here is the a and the log base a cancel out. Likewise, if you take log base a of a to the power x, these also cancel out and you just get x. And this is called the inverse property of logarithms. And we'll do some examples of this as well. So let's first start by giving equivalent exponential statements for the following logarithmic statements. So here we have 4 logarithmic statements, and we want to give the equivalence in exponential form. So when we say log base 3 of 9 is equal to 2, the exponential form of this is 3 to the second power is equal to 9. And so you can see that little diagram is quite helpful in doing this. So the equivalent exponential statement is this. In the second one, we have log base 5 of radical 5 equals 1/2. Once again, this means 5 to the 1/2 power is equal to radical 5. And this is, of course, true, right? Because we know that a 1/2 power is the same as the square root. The next log statement says log base 2 of 1/4 equals -2. So in exponential form, it means 2 to the -2 is equal to 1/4. And of course, this is also true. We know this because we've studied exponents. And finally, we have log base a of b is equal to k. So in exponential form, this will say that a to the k power is equal to b. So again, you want to be able to convert logarithmic statements into exponential statements with no trouble whatsoever. Now let's take a look at equivalent logarithmic statements. So here we have some exponential statements, and we want to convert them into logarithmic form. Now, I will admit that this is a little bit tougher to get used to, but basically, the number that you see here is the base of the exponential function. So 4 is the base, 10 is the base, 6 is the base, and a is the base. And that's the number that you're going to see on your logarithmic statement, right? So remember, your logarithmic statement, such as the one you see right here, has a base, and then it has the number that you are taking the log of. So the base is always this smaller number down below the logarithm. So let's keep that in mind as we do our conversions here. So when we say 4 to the 0 power is equal to 1, this is going to mean log base 4 of 1 is equal to 0. Now we can double check that by just doing the simple little conversion that we did previously. So we know from logarithms that this says 4 to the 0 power is equal to 1. So yes, this is the equivalent statement in logarithmic form. The next one, 10 to the negative 1 equals 0.1. This is going to be log base 10 of 0.1 is equal to negative 1. And you can check it for accuracy. The next one, log base 6 of the cube root of 6 is equal to 1/3. And finally, log base A of V is equal to K. So again, you just need to know the definition of a logarithm, and you should be able to easily convert log statements into exponential statements and vice versa. Next, let's talk about evaluating logarithms without a calculator. So let's go through these examples. In the first example, we have log base 5 of 125, and we want to know, what does this equal? Well, let's call it x, and let's see if we can figure out what x would be. So we know that this means that 5 to the x power is equal to 125. But we also know that 125 is 5 to the 3rd power. So from this, it's pretty clear that x must be 3. So in other words, log base 5 of 125 must be 3 because 5 to the 3rd power is equal to 125. So to get more of an intuitive sense of logarithms, logarithms simply focus on the exponent. So the 3 over here is the exponent required of 5 to get 125. Let's take a look at the next one. So we have log base 10 of 1 over 100. And the question is, what does this equal to? So we need to think, well, 10 raised to what power equals 1 over 100? Right? I mean, that's essentially what we're doing here. 10 to this power equals 1 over 100. Well, we know that 10 to the 2nd power is 100, but we want 1 over 100. So it must be negative 2, because 10 to the negative 2 means 1 over 10 squared, and that would be 1 over 100. So just by understanding what it means when you talk about a logarithm, we know that this must be negative 2. For the next one, we have log base A of a to the 4th power. And we want to know, what does this equal? Well, once again, this is going to equal something such that when you take this base and you raise it to this power, you are supposed to get this number. So this quite simply means a to what power is equal to a to the 4th? Well, 4, right? Because a to the 4th equals a to the 4th. So again, we can deduce just by simply knowing the definition of a logarithm that this must be equal to 4. The next one, we have 3 to the power log base 3 of 5. So here we can use the inverse property, which says that when you have the base 3 and you raise it to a power log base 3, the 3 and the log base 3 cancel out, and we simply get the number 5. And finally, we have log base 10 of negative 1. And the question here is, what does this equal? Well, this has no solution, because if you think about it, we're saying if you take 10 and you raise it to what power, how do you get negative 1? What power do you have to raise it to get negative 1? Well, quite simply, there is no power of 10 that gives you a negative number, right? Just think about that for just a minute. If I have 10 to the third power, we know that's 1,000. If I have 10 to the first power, this is 10. 10 to the negative 1 is 1/10. 10 to the negative 3 is 1 over 1,000. You are never going to get a negative number when you raise 10 to any power, no matter if it's a positive power or a negative power. So this expression is undefined. You can't take the log of a negative number. Now, if you go back to our definition, we would know that automatically just from knowing our definition. Let's take a look at that real quick. So in our original definition, it said that y is equal to log base a of x, and it said x has to be greater than 0. Well, x is the thing we're taking the log of, so this number here must always be a positive number. It cannot be negative. So if we knew that, then we wouldn't have to even figure out that last problem that we did. Right? So you could just look at this and say, well, this is negative, therefore we can't do it. It's undefined. Here we're asked to solve an equation involving a logarithm. And in the first equation, we have log base 4 of 16 is equal to x. And to solve for x here, I'm just going to change this into exponential form. So this means 4 to the x power is equal to 16. And from this, quite clearly, x has to be 2, right? Because we know that 4 squared is 16. In the second problem, we have log base 3 of x is equal to negative 2. To better understand this, I will put this in exponential form. In exponential form, this means 3 to the negative 2 must be equal to x. But 3 to the negative 2 is 1 over 3 squared. And 1 over 3 squared is 1/9. So we know that x must be 1/9. So again, the point here is that if you're asked a question about logarithms, you are going to lean heavily on the definition of that logarithm in terms of putting it into exponential form, because we understand this better right now. This is more familiar to us. Next, let's talk about common logs and natural logs. So the definition of a common logarithm is when we write y equals log of x. And when we say log of x, we mean that the base here is 10. So y equals log of x is equivalent to x equals 10 to the y. So really what's important here is to understand that log of x really just means log base 10 of x. So if you don't see a base on your logarithm, it's automatically a 10. The other important logarithm is what we call the natural logarithm. And the way we indicate a natural logarithm is we write ln instead of spelling the word log. So if y equals ln of x, this is understood to be the natural log, and it means here that x equals e to the y. So what we're saying here is that the natural log of x is the same thing as a logarithm with a base equal to e, right? That important number e that we talked about in the previous section. So anytime you see ln of x, you need to understand that this is the natural log of x. And when you read it, you really should say natural log instead of saying the letters ln. Okay, so let's get in the habit of calling this natural log of x. So in our next couple of examples, here we are asked to find the log of 10,000. And we want to do this without using a calculator. So remember, a log with no base here means the base is 10. So this is the same as log base 10 of 10,000. And we want to know, what does this equal? Well, it means that if you take 10 and you raise it to that power, you get 10,000. So 10 to what power equals 10,000? Well, powers of 10 are pretty easy. So if we have 10,000, notice that we have 4 zeros here. So it's 10 to the fourth power equals 10,000. So the log of 10,000 is equal to 4. In the next example, we have the natural log of e to the 1/2 power. And they're asking us to do this without a calculator, which means there must be a way to figure this out without using a machine. So here we need to remember that natural log means log base e. And we have log base e of e to the 1/2. So remember, when you have a log with a certain base followed up by an exponential with the same base, these cancel out and we end up just getting 1/2. Okay, so that's the inverse property of logarithms. And the third one, we have e to the natural log of a. Once again, this means e to the log base e of a. And once again, when you have the base e raised to the log base e, these cancel out and we just get the number a. Now, there are some logarithms that you cannot calculate by hand. You will need a calculator to do some calculations. Suppose, for example, I ask you to find the log of 67. Now, we know that this means logarithm base 10 of 67. But what is this equal to? Well, do you know what power of 10 is equal to 67? I don't think so, right? You know 10 to the first power is 10, and you know 10 to the second power is 100, but we're saying, what is the power of 10 to get 67? Well, we don't know, right? So we need a calculator for this. So in order to do this on a calculator, you simply need to locate the logarithm button on your calculator, which on this particular calculator is right here. You can see it, log. And you're just going to type the logarithm by hitting that button. And what will be displayed on the screen is a log with a parentheses. And then we'll type in 67, close the parentheses, and then we'll hit equals. Okay? And if you do that, this is what it looks like. So the log of 67 is 1.826074803. And that's an approximate answer. So if we round that to 4 decimal places, we would say that the log of 67 is approximately equal to 1.8261. Right? Again, that's rounding to 4 decimal places, which is very common. Now, what this means, let's just think about what this means. It means logarithm base 10 of 67 is 1.8261, approximately. That means 10 raised to the power 1.8261 is approximately equal to 67. So this is actually quite interesting because it allows us to find unique powers of 10, right? To get any number that we want. Now, natural logs work the same way. So let's suppose I want you to calculate the natural log of 8. Now we know that this means logarithm base e of 8. What is this equal to? Well, do you know what power of e gives you 8? No, of course we don't know that, right? So natural log of 8 is another one that we would plug into a calculator. Now the way you would do that is just locate the natural log key, which is this key on this calculator down here, and then just type in the number 8. So when I hit that key, we're going to see natural log with the parentheses. We put in the number 8, we close the parentheses, and we hit equals, and that will give us the approximation. And that looks like this. So you see here, if I type in the natural log of 8, we get the number 2.079441542. Rounding that to 4 decimal places, the natural log of 8 is approximately equal to 2.0794. Now, what that means exactly is logarithm base e of 8 is approximately 2.0794. And that means e to the power 2.0794 should be approximately equal to 8. And you can verify that on your calculator. So there will be times for you to use a calculator when approximating values of natural logarithms and also common logarithms. Now the question is, what would you do if you were asked to find logarithm base 3 of 17? What would this be equal to? Well, we're in a little bit of a bind here because we don't have a logarithm base 3 on our calculator. We only have base 10 and base e. So how do we deal with a base such as this? Let's talk about that now. So what we need to do this is something called a change of base formula. And there are two change of base formulas that we can use, and it doesn't matter which one you use. So if you want to change logarithm base a of x to something that you can type into your calculator, you can either say that it's equal to log base 10 of x divided by log base 10 of a, or you can say it's equal to the natural log of x divided by the natural log of a. It doesn't matter which of these two formulas that you use, as they both give you the same thing. So in this next example, they ask us to use the change of base formula to calculate log base 6 of 15. And here they want us to use the common logarithm. So using the common logarithm, we would say log base 6 of 15 is equal to the log of 15 divided by the log of 6. And all I'm doing is using this formula right here. But remember, if it's log base 10, I don't have to actually write the number 10 there. So what is log base 15, or a log of 15 divided by log of 6? We can type this into our calculator. And when you type this into a calculator, you can see that you get the result that we have down below here. And we'll round this to 4 decimal places. That's the typical rounding that we use. So this is approximately equal to 1.5114. Now, just to show you, you could have also used this other formula and you would have gotten the same thing. To do that, you would simply say natural log of 15 divided by the natural log of 6. And this is also equal to 1.5114. And I'll bring in the calculator now. So just for verification purposes, you can see that indeed this expression gives you the same answer. Now how about part B? Let's find log base 7 of 0.3 using natural logarithm. So they want us to use this formula. So log base 7 of 0.3 would be equal to the natural log of 0.3 divided by the natural log of 7. And if we put this into a calculator, we get negative 0.6187 when rounded to 4 decimal places. So this is approximately equal to negative 0.6187. So this change of base formula allows you to find any logarithm of any number. So it doesn't matter what the base is, you can calculate it with this change of base formula. Next, let's talk a little bit about graphs of logarithmic functions. So if you're graphing the logarithmic function f of x equals log base a of x, where a is a number bigger than 1, the graph looks like this. It will always pass through the point 1, 0 and the point a, 1. And it will be this increasing function. If you're talking about a logarithm where the base a is a number in between 0 and 1, it will be this decreasing logarithmic function. It will still pass through the point 1, 0, and it will still pass through the point a, 1, but now a is a number less than 1. Now, why does it have this particular shape? Well, it turns out that a logarithmic function, base a, is nothing more than the inverse of the exponential function with the base a. So let me bring in a graph of each of those functions so that we can compare. So as it turns out, y equals the logarithm base a of x is the inverse function to y equals a to the power x. So for y equals a to the power x, we know that that function passes through the point 0, 1, and we know that it also passes through the point 1a, right? And this is because a to the first power is equal to a. Now, the inverse function is the logarithm, and we know that there is symmetry across the line y equals x. And so this point on the logarithmic function has to be the point 1, 0. That's just the point that we get when we reverse the coordinates here. Also, on the other side here, we will have the point a1. So anytime you're asked to graph a logarithmic function, it is sometimes beneficial to first graph the corresponding exponential function and then to simply reverse the coordinates. So here we'll do an example where they ask us to graph f of x equals log base 2 of x. So the inverse function to log base 2 of x is the function y equals 2 to the power x. And we know how to get points on this function quite easily. So if I plug in the values from -2 to +2, we get the corresponding values for 2 to the x. So if I want to graph the function f of x equals log base 2 of x, we know that this function is the inverse of this function. So because it is the inverse, all it's going to do is reverse the coordinates on all these points. So instead of 2, 4, we will have 4, 2. Instead of 1, 2, we will have 2, 1. And then 1, 0. And then 1/2, -1. And finally, 1/4, -2. And then the graph is quite easy to get from there. All we need to do is simply graph these points. So we have the point 4, 2, 2, 1, 1, 0, 1/2, -1, and 1/4, -2. And what you should see is that the logarithmic function has this shape here. And as you move in closer to x equals 0, it approaches the y-axis but never touches it. And so this is the graph of the function f of x equals log base 2 of x. So again, to get the points here, it's kind of difficult to get these points just by looking at the logarithm. So just consider the inverse function, which is an exponential function, get those points, and then all you have to do is reverse the coordinates. That's the easiest way to get a table of values for a logarithm.